Dear students, in last class we discussed that if A congruence to B mod M, we tries to prove if A congruence to B mod M, then for any polynomial f with integer coefficients, we have to show that f of A congruence to f of B mod M. In last class we already proved the result is true for when n equals 0, means when f is when n be the degree of polynomial f. So in last class we already proved that the result is true for a constant polynomial and if f is a polynomial of degree 1. Now here we try to prove the result is true for any polynomial f with the integer coefficients as degree n. Now by induction, suppose the result is true for every polynomial f having degree n minus 1. That is, f of x equals, if f of x equals a0 plus a1x plus etc. plus an minus 1 x power n minus 1, then we know that f of a congruence to, then by induction hypothesis, we can assume that if f of x is a0 plus etc. plus an minus 1 x power n minus 1, then f of a congruence to f of b mod m. Now to prove the result is true for f with the degree n, let degree of f equals n. Let degree of f equals n. That means, then what is f of x? Then f of x is nothing but it is a0 plus a1x plus etc. plus an minus 1 x power n minus 1 plus an x power n. What is actually this one? a1x plus a0 plus a1x plus etc. plus an minus 1 x power n minus 1 is nothing but it is f n minus 1 of x plus an x power n. That means f of x is rewrite as f n minus 1 x plus an x power n. So what about f of a? Therefore f of a equals f n minus 1 a plus an a power n. And what is f of b? F of b is f n minus 1 b plus an b power n. Replace x by a and b respectively. But it is given a congruence to b mod m. Given a congruence to b mod m means m must divides a minus b. But if m divides a minus b, by the previous theorem or by we already proved that if m divides a minus b, m divides a raised to n minus b raised to n. So then m divides a raised to n minus b raised to n. That means m divides it is an into a raised to n minus b minus an into b raised to n. Okay, if m divides a raised to n minus b raised to n, then we can say that m divides a raised to n minus an b raised to n. Again by induction, we know that m divides f n minus 1 a minus f n minus 1 b. By induction, the result is true for every polynomial f with the degree n minus 1. Hence, by induction, we know that m divides f n minus 1 a minus f n minus 1 b. Also, m divides a raised to a power n minus a n b power n. Agree? Okay. Hence, therefore, m divides f n minus 1 a minus f n minus 1 b plus a raised to n minus a n b raised to n. You can associate. That means m must divide f n minus 1 a plus a raised to n. What is f n minus 1 a plus a raised to n? That is f n a minus of f n minus 1 b plus a b raised to n. That is f n b. So if you associate, then you have m divides f n a minus f n b. That means f n a congruence to, that means f n a congruence to f n b mod m. So that means the result is true for every polynomial f with integer coefficient having degree n. Hence by induction hypothesis, the result is verified. Enough. Okay. Now we go through some interesting results. That is, now let us go through some interesting result. That is, test for divisibility by 9. Test for divisibility by 9 means an integer n greater than 0 is divisible by 9. An integer n greater than 0 is divisible by 9 if and only if the sum of its digits in its decimal expansion is divisible by 9. If an integer n greater than 0 is divisible by 9, then the sum of its digits in its decimal expansion also divisible by 9. What is the decimal expansion of any number? If the decimal expansion of any number means, suppose n is any number, then its decimal expansion is, it is a0 plus 10a1 plus 10 square a2 plus 10 cube a3 plus etc. Okay, 10 cube a3 plus etc. Where if the digits of n decimal notations are, if the digits of n decimal notations are a0 etc. ak. So it is plus etc. plus 10 power k ak. Okay. N greater than 0. If n is divisible by 9, suppose that the digits of n decimals, the digits of n decimal notations are a0, a1 etc. ak, then n equals a0 plus 10a1 plus 10 square a2 plus 10 cube a3 plus etc. plus 10 power k ak. We also know that 1 complements to 1 mod 10. That's immediate. 1 complements to 1 mod 10. Sorry, 1 complements to 1 mod 9. This will be 9. 1 complements to 1 mod 9. Agree. What about our 10? 10 also complements to 1 mod 9. Sure. 10 minus 1. What about 10 square? 10 square also complements to 1 mod 9. 10 cube is complements to 1 mod 9, etc. So 10 power k complements to 1 mod 9. Agree. So from here, 1 complements to 1 mod 9 means a0 complements to a0 mod 9. Sure. If a complements to b mod m, ac complements to bc mod m. Comma 10a1. From second, 10a1 complements to a1 mod 9. Sure. From third, it is 10 square a2 complements to a2 mod 9. Okay. Yes, etc. The last one, 10 power k ak complements to ak mod 9. Agree? Yes. You can add vertically. What you get? a0 plus 10a1 plus 10 square a2 plus etc. plus 10 power k ak. That is a0 plus 10a1 plus etc. plus 10 power k ak complements to, come on, a0 plus a1 plus a2 plus etc. plus ak mod 9. a1 plus a2 plus etc. plus ak mod 9. Agree? What about the left side? Left side is nothing but n. So it is, that means n complements to a1 plus a2 plus etc. plus ak mod 9. N complements to that one. That means 9 divides n minus of a0 plus actually this is a0 plus a1 plus a0 plus a1 plus etc. plus ak. 9 divides n minus of a0 plus a1 plus etc. plus ak. Then it is divisible. If n is divisible by 9, means if 9 divides n, 9 divides of n minus this one, then surely that implies 9 divides of a0 plus a1 plus etc. plus ak. Okay. If 9 divides n, from here it is clear that 9 divides of this sum. So 9 divides n implies 9 divides this one. Reversely, if 9 divides a0 plus a1 plus etc. plus ak, 9 divides n. So when 9 divides n, 9 divides a0 plus a1 plus etc. plus ak. What is a0, a1 etc. ak? They are the digit notation of that the n. Then they are the digits of n. It's a decimal notation of That is A0, A1, etc. AK. The A1, A0, etc. AK are the decimal notations of the digit n. So 9 divides A0 plus etc. plus AK means 9 divides sum of its decimal notations. So when 9 divides n is implies n is implied by 9 divides the decimal notation of the digits n itself. Agree? So this is an interesting result. When n greater than 0 and divisible by 9, then if and only if n divides or the sum of its digits in the decimal expansion is also divided by divisible by 9. Okay. The same result is true for 9. If n greater than 0, that is the test of divisibility of 3. For any integer n greater than 0 is divisible by 3 if and only if the sum of its digits in the decimal expansion is divisible by 3 itself. Same arguments. Why? Because when A0, A1, etc. AK are the decimal notations of the digit n greater than 0, then we have 1 complements to instead of 9, here 1 complements to 1 mod 3. 10 complements to also 1 mod 3. Sure. 10 square complements to also 1 mod 3, etc. 10 power k complements to 1 mod 3. Then from here A0 complements to A0 mod 3, like 10 power k, AK complements to AK mod 3. Then you can add vertically. Finally you will have n complements to A0 plus A1 plus A2 plus etc. plus AK mod. Instead of 9 it is 3. So instead of 9 here it is 3 divides n minus of that one. When 3 divides the n, then 3 divides the n, 3 divides the sum A0 plus etc. plus AK. That means 3 divides sum of its decimal notations. Agree. So the result called for 9. That is the test for divisibility of 9 and test for divisibility of 3 itself. Agree. Okay. So now let us consider another result. It is Fermat number. Now we consider another one. It is Fermat number. What is a Fermat number? Fermat number means a number is of the form. A number is of the form 2 power n plus 1. A number is of the form 2 power n plus 1, where n is an integer. A number is of the form 2 power n plus 1. So this number is said to be a Fermat. So what is the first Fermat number? Then it is f naught. F naught equals 2 power 0. When n equals 0, it is 2 power 0 plus 1. 2 power 0 plus 1 means it is 3. Okay. What is f1? F1 is 2 power 1 plus 1. It is 5. Enough. What is f2? F2 is 2 power 2 plus 1 means 2 power 4. What is 2 power 4? 16 plus 1, 17. What is f3? F3 is 2 power 3 plus 1, 2 cube 5, 2 power 30, 2 power 5 plus 1, that is 2 power 5 plus 1. So it is 2 power 2 cube plus 1, 2 power 2 cube, so 2 power 8 plus 1. What is 2 power 8? It is 256 plus 1, 2 power 2 cube plus 1. What is 2 power 2 cube plus 1? 2 power 2 cube means 2 power 8. 2 cube means 8. Okay, so 2 power 8 plus 1. And what about F4? F4 is 2 power 4 plus 1. What is 2 power 4 plus 1? It is some 65,537. So consider all of these numbers. All of these numbers are primes. But we cannot say that 2 power n plus 1 is always a prime. The Fermat number is not always a prime, but the first term F0, F1, F2, F3, F4, first 5 these terms are prime numbers. What about actually F5? F5 is not a prime. It is actually divisible by 641. F5 is divisible by F5, which is divisible by 641. You can calculate by what is F5 when n equals 5. When n equals 5, F5 is 2 power 5 plus 1. Okay. Yes. What is when n equals 4? That is F4, 2 power 4, 16. Actually, 2 power 4, this one, F4, 2 power 4 plus 1. Agree? 2 power 4 plus 1 means, when n equals 4, 2 power 4 is 2 power 16. You can write this 2 power 16. 2 power 16 can be rewrite as, it is actually 102 into 641 plus 154. You can calculate, you can compute this one. 2 power 16 can be rewrite as 102 into 641 plus 154. So from here, what is 2 power 16? 2 power 16 is congruence to 154 mod 641. Okay, 154 mod 641. And what about 2 power 6? Again, when n equals 5, n equals 5 means n equals 5 means 2 power 5 plus 1. 2 power 5 means 2 power 32 plus 1. Agreed? What is actually 2 power 32? 2 power 32 means 2 power 16. 2 power 32 means 2 power 32 means 2 power 16 whole square. Okay. So 2 power 16 whole square is congruence to 154 whole square mod 641. 154 whole square mod 640. Okay, but what about 154 whole square? It is 23,760. It equals 23,716 mod 641. Enough, mod 641. That is, you can again rearrange it as 2 power 16 whole square. 2 power 16 whole square is congruence to, that is, which is congruence to, again it is 640 plus, it is 640 plus, now 36 into 641, 36 into 641 mod, 36 into 641 mod 641. Okay, that means 2 power 32 is congruence to 640 mod 641. 640 mod 641. Okay, therefore 2 power 32 plus 1 is congruence to 641 mod 641 mod 641. So 2 power 32 plus 1 means 2 power 5 plus 1 is divisible by 641. So Fermat number means a number is of the form 2 power n plus 1. So it's first of all F0, F1, F2, F3 and F4. All of these 5 terms are primes, but the next term F5, which is not a prime number, which is divisible by 640. Okay. Now let us consider the common non-zero factors. There is a result according to this congruence. The common non-zero factors cannot be cancelled from both the members of the congruence. For means, we know that 48 is congruence to, what is 48? 48 is congruence to 18 mod 10. 48 is congruence to 18 mod 10. Sure. Okay, 48 is congruence to 18 mod 10. But 48 and 18, 6 is common factor. So 8 congruence to 3 mod 10, which is a wrong statement. 18 is not in congruence to 3 mod 10. So the common non-zero factors cannot be cancelled. In case of congruence, the common non-zero factors cannot be cancelled. We can prove that by using this simple example. So, but we can cancel in this common factor if it are subjected to certain conditions. If C positive, come to this argument, if C is positive, A congruence to B mod E, A congruence to B mod M, then AC congruence to BC mod MC. If C is positive and A congruence to B mod M, then AC is congruence to BC mod MC. A congruence to B mod M if and only if AC congruence to BC mod. That's immediate. Why? When A congruence to B mod M. A congruence to B mod M, that means M divides A minus B. M divides A minus B means MC divides AC minus BC. MC divides AC minus BC means AC minus BC congruence to 0 mod M. That means AC congruence to BC mod M. Sorry, BC mod MC. AC congruence to BC mod MC. Then reversely, when AC congruence to BC mod MC, AC minus BC is congruence to 0 mod MC. That is MC divides AC minus BC. That means M divides A minus B. That means A congruence to B mod M. So when A congruence to B mod M and C is positive, then that implies and is implied by AC congruence to BC mod MC. Then in previous example we say that I already said that the cancellation of common non-zero terms is not possible in case of congruence, but it is possible in some terms, like cancellation law hold. If AC congruence to BC mod M and if D is the GCD of M and C, then A congruence to B mod M by D. That is the next result. The result is proved in our next class. So, thank you.